All right, welcome. Today, we are diving into a really crucial step in database design. We're going to talk about how you take that perfect entity relationship diagram you've planned out and turn it into a real working database that a computer can actually understand and use. So let's get right into it. I always think of an ER diagram as an architect's blueprint. It's this beautiful, detailed plan that shows every room, every connection, every little detail. But you can't live in a blueprint, right? You have to actually build the house. That's exactly what we're doing here. We're taking the design and building the real thing, the relational tables that are the true foundation of your database. So here's our game plan for today. We'll start with the why we even do this. Then we'll get into the real meat of it, translating your entities and mapping your relationships. After that, we'll put it all to the test with a hands-on example, and we'll wrap up with a super handy cheat sheet so you can remember all the key rules. So first up, why do we even need this conversion step? I mean, the diagram looks great. Well, it's pretty simple, actually. ER diagrams are fantastic for us humans to visualize and design a database. They're a conceptual model. But the systems that actually run everything, MySQL, Oracle, SQL Server, they don't speak diagram, they speak tables. Our whole mission here is to follow a clear set of rules, a logical process to translate every single entity, attribute, and relationship into a set of clean, efficient tables. This isn't guesswork, it's a system. So let's get started with the most basic building blocks. First on the list, entities. These are the main things in your system. The nouns, like student, product, or employee. Getting this part right is absolutely fundamental to the whole process. We're going to follow 3 core rules for handling our entities, and it all depends on what kind of attributes they have. Let's just break them down one by one. Okay, rule 1. This is the easy one, our starting point. If you have a strong entity with just simple, single-valued attributes, like a student with a name and an ID, it becomes one table. That's it. The attributes become the columns, and that unique identifier becomes the primary key. One entity, one table. Done. So what if you have a composite attribute, say an address that's made up of a street, a city, and a zip code? Does that mean more tables? Nope. It's still just one table. We flatten it. The address attribute itself goes away, and its smaller parts, street, city, zip, they just become their own individual columns in the table. Easy. Okay, now this is where it gets interesting. Multi-valued attributes. This is a real game changer. Let's say a student can have multiple phone numbers. This forces us, to create a brand new separate table. The original student table holds the main info. The new table is just for the phone numbers, and here's the key. It uses the student's primary key to link back to the original student. We call that link a foreign key. So the takeaway is simple. See a multi-valued attribute? You're going to need an extra table. All right, we've handled our building blocks, the entities. Now it's time to build the connections. We're going to translate the relationships, the lines between the boxes on our diagram. This is where we can really start to optimize our database and make it efficient. Let's kick things off with the most distinct relationship type, the many-to-many. The classic example is students and courses. One student can take many courses, and one course can have many students. Makes sense, right? So how many tables does this require? The answer is always 3. No exceptions. This is one of those rules you can just lock in your brain. A many-to-many relationship will always become 3 tables in your database. And here's how that works. You get one table for your first entity, say students, one table for your second entity, courses, and then you create a third, brand new table just for the relationship itself. Think of it like a bridge or a junction table, and its primary key is made up of the primary keys from the 2 tables it connects. Okay, moving on to the very common one-to-many relationship. Think about a department that has many employees. Unlike that many-to-many case, we can actually be a bit more clever and efficient here. That's right. For a one-to-many, we only need 2 tables. We get to optimize by merging the relationship information right into one of the entity's tables. Now, here's the trick to this optimization. You take the primary key from the one side of the relationship, in this case the department ID, and you add it as a new column in the table on the many side, the employee table. This new column in the employee table is a foreign key. It points back to the correct department for each employee. So the relationship table basically gets absorbed into the many side. Pretty neat, huh? Let's quickly round things out with a few more rules. For a one-to-one relationship, you still use two tables, but you get to choose. You can merge the relationship into either side. Then there's total participation. If an entity has to be in a relationship, we enforce that by making its foreign key field not null. And finally, a weak entity, one that can't exist on its own. It always gets its own separate table, which includes the primary key from the strong entity it depends on. Okay, theory is great, but let's put these rules to work. We're going to run through a practical example to figure out the absolute minimum number of tables we'd need for a specific ER diagram. So here's our setup. We've got three entities, M, P, and N. M has a one-to-many relationship with P, and P has a many-to-one relationship with N. Also, pay attention to the constraints. M must participate in its relationship, and so must N. So, based on everything we've just discussed, what do you think? How many tables do we need here? The minimum number required is 3. Now let's see exactly how we get to that answer. Okay, let's break down the solution. It's a really interesting example of how the rules can be applied. We have that one-to-many from M to P, and that many-to-one from P to N. In this particular solution, the relationship R1 gets merged into the M table, and the relationship R2 gets merged into the N table. This leaves P, which is the entity caught in the middle of both relationships, as its own standalone table. So that gives us our 3 tables, a combined table for M, a standalone table for P, and a combined table for N. It really shows how specific constraints can guide you to the most optimized final structure. All right, that was a great little workout for our brains. To make sure all these concepts really stick, let's wrap this up with a simple, powerful cheat sheet that covers the most important rules you'll need. Honestly, this is the core of it right here. If you see a multi-valued attribute, boom, you make a new table. See a many-to-many relationship, that's always going to be 3 tables. Got a one-to-many? You can optimize that down to 2 tables by merging. And a weak entity? It gets its own table linked back to its parent. This is your go-to guide for any ER conversion. And for a final thought to leave you with, we spent this whole time trying to find the minimum number of tables. But when might you actually want to break these rules and intentionally use more tables than you need? It's a little hint at more advanced topics, like denormalization for performance or clarity. Definitely something to chew on. Thanks for joining me today.